तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, this was the parameter in terms of which we were deciding whether classical statistics should be used in a given situation or quantum statistics, and what we derived was that if this quantity is less than 1 implies that classical statistics is applicable. And I pointed out that it is indeed much less than 1 for normal gases at room temperature, for instance. So, the two ways in which this could change, one of them is if you have very high temperatures, then you are in the classical regime. If you are at very low temperatures, then this could go the other way, the inequality could be violated, and then of course you have to go to quantum physics. Or if the density is very high, if the number density is very high, which is what happens in astrophysical context, the number density becomes very high, even though the temperature is high, it is not high enough, and then you have what is called a very degenerate quantum system or quantum gas, and you have to use different techniques. We will do this in the next course a little bit. This is a dimensionless number because ultimately it arose from the following. It arose from the de Broglie wavelength or thermal, lambda thermal, divided by the mean separation, and it just said if lambda thermal, the fuzziness in the position of each particle is much smaller than the interparticle separation, you could get away with classical statistics. On the other hand, if it is very spread out, then the quantum effects become important, and then the effect of exchange, the indistinguishability of particles plays a predominant role, and the statistics changes. So that is the idea. A very useful parameter to tell when you should have classical statistics and when you should have quantum statistics for these systems, for gases and things, fluids and so on. There are other systems like spin systems, which we will look at in the next course, where the system is intrinsically quantum mechanical, and then there could be temperature regimes where it becomes effectively classical for various purposes. We will look at that too. I promised earlier that I would spend a little bit of time on probability distributions, and maybe this is a good time to do this because we postponed it. What I would like to do after this is to go on to a real gas like the van der Waals gas, and then talk a little bit about the Weiss molecular theory of ferromagnetism, and then we move on to the next topic. So this is what the curriculum says, the syllabus says, and we will stick to that. So let me spend a few minutes talking about probability distributions. You probably already know a lot of this, many aspects of it. So let us do this in a kind of informal way. So if I have a random variable, some kind of random variable x, could be discrete valued, in which case all that I am going to write down, integrals would be replaced by sums. But if it is continuous, which is the more interesting case in many situations, then there exists a probability, we assume that there exists a probability density function p of x. This is an assumption. Of course, all random variables do not have to have a well behaved probability density function. Whenever it does, we are going to assume some properties on the part of this p of x. The first part of course is p of x is greater than or equal to 0, can't be negative, and the second thing we are going to assume about it is that it is normalized to unity. In other words, this is such that over the range of whatever it be, dx p of x equal to 1. So total probability is 1. You can always also define the cumulative probability distribution, sometimes called the probability distribution itself, but it is actually the cumulative probability distribution or distribution function. We need a name for this, so we need a symbol. Let me just call it p of x. This is an integral up to the value x dx p of x. So let us be careful and put px prime from minus infinity, assuming that the lower limit of integration is minus infinity or whatever is the lower bound. Okay. Now what is the meaning of this? This is equal to the probability that your random variable, so if I call this a capital X, call this p of capital X, it is the probability that the random variable is less than equal to this given value capital X. So it is the area under the curve from minus infinity up to whatever point you stop, and that is the total probability that the random variable has some value less than or equal to this prescribed value. And p of capital infinity is of course 1 by normalization. Physicists most of the time use this, talk about this, and the cumulative probability distribution is an integral over this density, but it is not as frequently used in physical applications as the probability density function itself. I should also caution you that very often in the physics literature this quantity itself is called the probability density, this quantity itself is called the distribution function, but it is actually not the distribution, it is the density, right? But then very loosely one says, for instance, when you say Maxwellian distribution of velocities and you write a Gaussian down, that Gaussian is a probability density function, it is not the distribution function. So that is a typical example, the Maxwellian distribution. It says that the probability density that any Cartesian component, say v sub x, of the velocity of a particle in thermal equilibrium, in a gas in thermal equilibrium, a classical gas, this quantity is given by e to the minus mvx squared over 2 k Boltzmann T at absolute temperature T, and there is a normalization factor which is m over 2 pi k Boltzmann T to the power half. So p of Vx dVx is the probability that the velocity x component has a value between some Vx and Vx plus dVx, and if you plot it, this is the famous Gaussian, which is a picture like that, and this is V sub x, this is p Vx, and similarly for the y and z components. Okay. This is not the distribution of the speed, which is modulus of the velocity vector, this is just the x component or the y or the z component. Okay. Now what is the cumulative distribution function? P curly p of Vx, this quantity would be an integral over this guy minus infinity up to Vx e to the minus m Vx prime squared over 2 k Boltzmann T dVx prime multiplied by the normalization. And what does the graph of this function look like? It starts at 0 at minus infinity and goes to 1 at plus infinity. So if you plot it, it is the area under the curve up to whatever point. So from minus infinity up to this point, the area total area under the curve is unity. So if I plot this function, here is Vx and here is P of Vx. It starts at 0 and goes to unity at plus infinity, and it crosses the axis at half, because half the area is on the area to the left of this axis is exactly a half. So this is what the integral density function looks like. That is the cumulative distribution function. There is a name given for this function, the integral of a Gaussian up to some point x. It is related to what is called the error function, and this is a special function. We are not going to go further into this. So there are tables of these error functions. So it is clear that this guy is normalized in such a way that p of minus infinity is 0, p of 0 equal to half, and p of infinity equal to 1. It is a non-negative function, and it is an increasing function. It is a non-decreasing function certainly. As you increase Vx, it monotonically climbs up towards 1. Okay. That is not as useful. The error function is not as useful as the density itself, which is a Gaussian and with which you can do things, you can do a lot of things. This Gaussian. So this is a very simple physical example of where a Gaussian appears, and appears all over the place, and we will see why in a while. Let me go back and define a few quantities with regard to probability density functions themselves. Well, I will denote the mean value of this variable by x, the mean value by x squared, the mean square value by x squared, the nth moment by xn, etc. These are the moments of the distribution, moments of this random variable x, and what I need is a formula to write it, and of course I have a formula, because if I x to the power n, as you know, is integral over the range of x dx p of x to the power n, assuming this is a normalized density. So I do not divide by the integral of that. Now it is useful to consider not individual moments, but what is called a moment generating function. So let us define a moment generating function, and let me call it m of u. There are lots of notations used. This is equal to a power series n equal to 0 to infinity, whose coefficients are just these quantities. By definition, this is the generating function. It is a power series in u, in this auxiliary variable u, and the coefficients of the coefficient of u to the n is the nth moment of this random variable over n factorial. It is also clear that you could put this u inside here, because u is not a random variable but just an auxiliary variable, and then this is an exponential series. So it is clear that this could also be written as equal to the average value of e to the power ux, because if I expand this term by term, the nth term is just u to the power n average x to the power n over n factorial. It looks like a sort of Fourier transform kind of thing, except you have got a u here. Well, you could also define the following. You could also define what is called the characteristic function, corresponding to the density p of x, and let us call it p tilde of k. This is an integral from minus infinity to infinity dx e to the minus I kx p of x. This is the Fourier transform of the probability density function. But you can also relate it to this, because notice that this is also equal to the average value of e to the minus I kx. X is the random variable, k is an auxiliary variable, the Fourier transform variable. So the Fourier transform of, incidentally this I have used a particular convention for the Fourier transform. You know that you can put a 1 over 2 pi here, or a 1 over root 2 pi, or this could be a plus sign, etc. So I have defined it such that to go from x to k I have no factor here and a plus and a minus here. So if I want to write p of x, it is equal to integral dk e to the plus I kx p tilde of k divided by 2 pi. Okay. So that is my convention, and the thing to notice is that the Fourier transform of this distribution could also be regarded as the average value of e to the minus I kx over all realizations of the random variable x. But it is also obvious that it is also immediately obvious this is equal to m of minus ik. So instead of u I put minus ik, I get exactly the same thing. So the characteristic function is nothing but the moment generating function evaluated at a pure imaginary value of the argument. Now what is it for a Gaussian? Well, we haven't come to a Gaussian yet, I will do so very shortly. Very often it turns out that it is useful, since this is the expectation value of an exponential. This is very reminiscent of what we did when we defined the free energy. There you had a whole lot of exponentials, the Boltzmann factors, and I said you could write it as a single exponential with some effective variable there, with energy there. And the same idea is actually, the idea is borrowed from statistics, because you could also write m of u could also be written as e to the power some other function k of u, which is e to the power summation n equal to 1 to infinity some kappa sub n u to the n over n factorial, because it is clear that this thing here is going to have all powers of u appearing in it, which you could also write in this form, in this representation. Then it would immediately imply that k of u equal to log m of u, and this is equal to n equal to 1 to infinity kappa sub n u to the n over n factorial formally. So it is again a power series, and the question is, what are these coefficients kappa sub n, and this number kappa n equal to nth cumulant of the distribution. In the older statistics literature, these things used to be called semi-invariants. I will explain the meaning or the reason for introducing this quantity, but it is called the cumulant of the distribution, and they are related to the moments through this relationship here. In fact, you can write the cumulants in terms of the moments of the distribution. So let us see what that relationship is. Just a little bit of playing around with this will tell you what these quantities are. K1, the first cumulant, turns out to be the average value itself, the first moment itself. So let me use a symbol for this, equal to mu, the mean value of x. The first cumulant is just the first moment itself, and that is very trivial to see from here. The second moment, K2, the second cumulant, turns out to be x squared minus x the whole squared, which is the variance. So this is also equal to the expectation value of x minus mu the whole squared. It is the variance, so it is the mean value of the square of the deviation from the mean, also called the variance. So let us use a symbol for it. So this is beginning to tell us what these cumulants are doing, and I will explain what the significance of these quantities is. The third moment, K3, the third cumulant, kappa 3, is equal to x minus mu the whole cubed. It is the mean value of the cube of the deviation from the mean. Incidentally, these quantities x minus mu, so these quantities x to the power n are the moments. These quantities x minus mu to the power n are the so called central moments. They are the moments about the mean. So it is very often convenient to shift to the mean. If the mean is systematically changing with time, for instance, it is convenient to remove that secular variation and then look at only the fluctuations. So this is what the central moments are, and the third cumulant is the third central moment also. The fourth is not. Kappa 4 equal to x minus mu to the power 4 minus 3 times x minus mu the whole squared, the whole thing squared. This is the variance and it is squared once again, so the dimensions come out right, and you have to subtract it 3 times that from the 4th central moment, and that is equal to the 4th cumulant, and so on. So there are standard formulas which will tell you what kappa n is in terms of the nth moment, n minus 1th moment, and so on all the way down, which you get simply by comparing on both sides. So write m of u in that form, take its log and then compare it power term by term in the power series of, obviously this guy has some radius of convergence in u, in the u plane, so everything is valid inside the radius of convergence. When you have a power series, you must treat the function defined by a power series as a function of a complex variable, and it is absolutely convergent inside some circle of convergence, and then you can integrate, differentiate term by term, etc., etc. So inside the circle of convergence a power series converges absolutely, and you can do all sorts of manipulations with it, and you can compare coefficients, etc. So I have assumed that there is a finite radius of convergence of this quantity. Okay. So within that radius of convergence this is perfectly alright, and I have kept u real, I mean I do not have to, as you can see I can go to pure imaginary values and so on. The point is this is a function of some, this is an analytic function in the neighbourhood of u equal to 0, it is guaranteed to be an analytic function with some radius of convergence. Okay. Now what is the formula, how to invert it? Well, that's not very hard. What is the advantage of finding this? Well, it is obvious that if I differentiate n times m of u over du to the power n, if I differentiate this guy, all the terms less than power n will disappear if I put u equal to 0. So if I differentiate this and put u equal to 0, I differentiate the first time with respect to u, I get an n, next time n minus 1, and that keeps cancelling this, so it is clear that this quantity is in fact equal to x to the power n. So that is the inversion formula. You could also write it as a contour integral around the origin in the u plane in the usual way of inverting a Taylor series. This is like a power series representation of this analytic function. Similarly here too, kappa n could also be written as equal to dn over du to the power n, k of u, the cumulant generating function evaluated at u equal to 0. So formally you can always invert the power series in this form. Now what is the physical meaning of these quantities here? The moment, of course the first moment tells you where the mean value is, the second moment, the variance tells you the spread about this central value, the first measure of a spread. The third gives you the skewness, because if this is symmetric, if this distribution is symmetric about its mean value, then this cube band average value vanishes, but if it is not, then this tells you the skewness, how much is it to one side or the other. A distribution, suppose the mean is 0 for example, a distribution which looks like this is a skew distribution. So if this is the mean value, this is the mean value, there could be more of it on this side, it should not be so fat, it could look like this, and maybe this side tapers off more slowly or something like that. These are skew distributions. And the third moment, this quantity here is a measure of the skewness or asymmetry of the distribution. If of course it is a symmetric distribution about its mean, then this is 0, and all odd central moments would vanish if it is a symmetric distribution about its mean. The physical meaning of the fourth is not so obvious. What it does is the following, and with reference to a symmetric distribution it has got the following meaning. So suppose you have a symmetric distribution, this is the mean value say, and it is symmetric about the mean, so no skewness here. Then this width here is proportional to the square root of the variance. The standard deviation measures how fat it is. Okay. What this guy does is to measure the departure from a Gaussian distribution. This quantity, as we will see, is exactly 0 for a Gaussian distribution. The fourth cumulant is exactly 0 for a Gaussian distribution. So if that number kappa 4 is positive, what it implies is that, as you can see, this is the fourth power sitting here. So large values of x are going to dominate in the fourth power. So this means that your distribution is such that the dominance of large values of x is greater than that of smaller values of x, which means that it is in some sense fatter than a Gaussian. More importance is being given to larger values. This is if so let me schematically say, this is if kappa 4 equal to 0, this is if kappa 4 is greater than 0 positive, but it could also be negative. There is nothing that says that this fourth cumulant has to be positive or negative. It could be negative. If it is negative, it means that this distribution is leaner than a Gaussian. More importance is being given to smaller values here, and it is leaner, and that is the reason why this quantity here becomes negative. So this is leaner than a Gaussian, and this has a name. It is called leptokurtic, and this guy has a name. It is called platykurtic. The distribution, and this quantity kappa 4 divided by kappa 2 whole squared, this is the square of the variance on this side, it normalizes by dividing by this square. This quantity here is called the excess of kurtosis for a probability distribution. So in a sense, in empirical usage, the first 4 moments kind of tell you more or less all that you need to know at a first approximation at least about the distribution. Of course, in principle you need to know the entire set of moments, you need to know an infinite number of pieces of information to be able to reconstruct the distribution, and this is a central problem of statistics. Given the moments, can you reconstruct the distribution or not? And there are conditions, necessary and sufficient conditions when you can do this. It is a little bit like asking, if I give you all the Fourier coefficients of a periodic function, can you reconstruct the function? I give you a discrete set of piece of information, can you reconstruct a continuous function? And the answer is, under certain circumstances, is yes, and it is the same sort of thing. This is called the problem of moments, and there is a very excellent text, I have forgotten the name now, it is called the problem of moments, and it was probably written in the 1920s or 1930s or something, and it is by Shabat and Tamarkin. It is called the problem of moments. It's repays reading, because this is a very classic book in statistics, many such very good books, and this is a particularly good one. So again, to repeat myself, the first 4 moments or the first 4 cumulants essentially tell you more or less what the distribution is like in practice. Now the question is, where does the Gaussian come in? What does that look like? And that is an interesting thing. I already mentioned that the Gaussian has the cumulant, fourth cumulant equal to 0, and K3, it is about the center, of course it is distributed symmetrically, so it is also 0. So only kappa 1 and kappa 2 are relevant. So let us see what the Gaussian is. Or normal. In a normal distribution, it is a 2-parameter distribution. In the normalized probability distribution for a random variable running from -infinity to infinity is the following. It is 1 over square root of 2 pi sigma squared e to the power minus x squared over 2 sigma squared, and x is on the real axis. This is normalized to 1, but I put the mean equal to 0. So for a general mean, it is actually this x minus mu whole squared over 2 sigma squared, and x equal to mu x minus mu whole squared equal to sigma squared, where the variance is sigma squared. Okay. One can take its moment generating function, or its compute what the Fourier transform of this quantity is, and it turns out that p tilde of k equal to m of minus I k in this case is not hard to do. You need a Fourier transform of a Gaussian, and many of you may be aware that the Fourier transform of a Gaussian is also a Gaussian in its turn, and this is equal to minus I k mu minus k squared sigma squared over 2, okay. Or if you like, m of u equal to e to the power exponent of something. This thing, m of u is e to the power mu u plus half sigma squared u squared. So the Gaussian is a particularly simple moment generating function. It is exponential of a polynomial in u which is stops at the quadratic level. So this immediately tells you, this implies that k of u equal to log m of u, and that is equal to mu u plus half sigma squared u squared. So for a Gaussian, and only for a Gaussian, the first moment is mu, the first cumulant is mu, the second cumulant is a variance sigma squared, and all the higher cumulants vanish identically, all of them, not just the third or fourth, but everything vanishes identically, and that is a great help, that is a very great help. Now why do I need the cumulants, why not work with the moments itself? The reason has to do with the fact, if you are looking at a single variable, a single random variable, then whether you use moments or cumulants is not very significant, does not matter, and the cumulants are helpful because you give some interpretation to them, as I did a few minutes ago, but you see most of the time you are concerned with sums of random variables. Linear combinations of random variables are probably even more complicated functions of random variables. Then look at what happens. Suppose you have two random variables and you want to ask, and they are independent of each other, and you want to ask what is the probability distribution of the sum of these random variables. Then what would you do? Well, so let us suppose you have two variables x1 and x2, and they are independent random variables, independent random variables. So they vary independent of each other, and I would like to know what is the probability distribution of the sum of these two random variables, some linear combination of the two random variables. So suppose this has a probability distribution or density p1 of x1, and this is p2 of x2. Then I ask, what is the probability density p of z, z equal to x1 plus x2. Let us look at the sum to start with. Okay. What should I do? Remember, these are independent of each other completely, x1 and x2 vary independently, and we look at several examples. Let me ask the following question. Suppose I have a variable x1 p of x1. Let us suppose this variable runs only between 0 and 1, and it runs uniformly between 0 and 1. So here is a random variable which can take on uniformly any value between 0 and 1, or be in any small interval dx in 0 and 1 with equal probability. It is a uniform distribution normalized to unity. So that is the probability density function. It is 0 outside here, 0 outside there, and it is 1 in between. And let us suppose x2 is another such variable which is also identically distributed. So p of x2 is also in this form, 0, 1, x1, it stops at 1. What is the distribution of the variable x1 plus x2? Now, would it be uniform?
No, it's not uniform.
Well, Gaussian, it's not going to happen now because there is just two such variables, right? So would it be uniform? First of all, this random variable z x1 plus x2, it runs from 0 to 2 now, because you have a sum and its maximum value is actually 2, but you could take x1 plus x2 divided by 2 and then of course that brings it back to 0 to 1. What would it look like? Think of it this way, I have 2 coins, I toss one, the probability of head or tail is half, the other one the probability of head or tail is half, but now if I toss both I have 4 possibilities, I have head head, tail tail, head tail, tail head, and what does the distribution look like? It looks like a quarter quarter half, right. You certainly have a greater probability that you have a head and a tail and a head, it does not, because you do not care which one is a head and which one is a tail, right. So at once you have more acceptable microstates in between than at the ends. So here if you say that the sum of the two z equal to x1 plus x2 and you ask what does the distribution of it look like, now p of z, I am sorry I am using the same symbol p here, I should use another function, it is a different function here. So we can well, let us call this p1, this is p2 and then this p of z, this will go up to 2 and it will start at 0, the area under the curve must be equal to 1. It is clear immediately that the region near 0 is not going to be weighted as much as the region near 1, because for it to be near 0 both x1 and x2 have to be near 0, and for it to be near 2 both x1 and x2 have to be at the extreme at 1. So it is a lot more likely that when this fellow is around here the other fellow is somewhere here and so on. So it is clear that it's the distribution is going to go look like this. You add one more variable and then the range is from 0 to 3, and what would then it would start looking like would be, if you had 3 such variables, it would do this up to 3. You add one more, it is going to start broadening out, and at the same time it is going to get more and more smooth as you go along, and after a while you can't tell the difference between this and a smooth curve, and you have a very large number of them, then the whole average also shifts towards n or n over 2, but you subtract that n over 2, then this thing starts looking like a Gaussian, provided you scale the variable properly, and that is what the central limit theorem says, and I will explicitly state this theorem. So you can already see that building up from here. The fact that when you add a whole lot of random variables, the probability that all of them are at one extreme or at the other extreme is small, but then lots and lots of accessible microstates in between, and therefore the density sort of peaks up. This is the gist of all these statistical theorems. So let us write this expression down and you will see the usefulness of cumulants here. This quantity is equal to a sum over all possible x1s, a sum over all possible x2s times the probability that it is x1 between x1 and dx1, that is the value of probability density at some point p2 of x2, but then there is a constraint which says that x1 plus x2 must be equal to your given number z. So what should I put? I should integrate over x1 and x2 subject to the statement that the sum of x1 plus x2 is some given number z, and then of course as z changes it becomes a function of this. So how do I impose this constraint? How will I impose the constraint that x1 plus x2 must be equal to z? Delta. So I should put a Dirac delta here, delta of z minus x1 plus x2 subject to that constraint. So that is my definition of the probability density, okay. And I have to do this integral, and of course this depends on what the ranges of these fellows are. The delta function may fire, may not fire, I have to be careful in doing this. So in the example I gave between 0 and 1, I urge you to do that, because there what happens is, if you plotted x1 here and x2 here and I plot x1 plus x2 equal to z, this is a straight line whose slope is -1. So in fact this is the straight line x1 plus x2 equal to 0. This is the straight line x1 plus x2 equal to 1 if this is 1, and the other guy is 2 and so on. So now when you are integrating between from x1 from 0 to 1, x2 from 0 to 1, you have a square over which you have to integrate, but the constraint is that x1 plus x2 must be equal to z. So if you take some z between 0 and 1, this is the constraint. Then it is clear that when you do the integral over one of the variables and get rid of the delta function, the other variable must be in such a range that the delta function fires. So this is the cutoff in your x1 when you are doing the x2 integration, and as this straight line moves up to 2, this is x1 plus x2 is 2, you can see the range over this is smaller, then it increases, then again becomes smaller, and that is the reason for the triangular shape, and after it crosses the diagonal it is a different range. So earlier the range in x1 was this, but at this stage the range in x1 is from here to there, so there is a little jump in the slope, and this is the reason why this jump occurred. So it is clear that you can formally use the delta function, but you got to be very careful to make sure that it really does fire, that it is within the range of integration. But formally, if these fellows go from minus infinity to infinity for example, then the delta function always fires, and I could write this as integral dx1 p1 of x1 p2 of z minus x1. Now what does that look like? What sort of integral is that? It is a convolution integral, so it is obvious immediately the corresponding Fourier transforms will multiply. So it is immediately obvious that if implies that p tilde of k equal to p1 tilde of k, p2 tilde of k, where these are the characteristic functions of the two distributions or densities p1 and p2, or if you like it says m of minus ik equal to m1 of minus ik times m2 of minus ik, where m1 and m2 are the moment generating functions of the variables x1 and x2 and m for the sum. Now that is a product. Now what should you do to get this product simplified? Take logs, then it adds up. So it immediately implies this thing here implies that the moment generating function of the cumulants, or the cumulant generating function k of minus ik equal to k1 of minus ik plus k2 minus ik. Each of these is a power series in k or u, and therefore you can compare coefficients, and it immediately tells you that kappa n for the sum is equal to the sum of kappa n for the first variable plus kappa n for the second variable. So the cumulants add up, the moments do not. You have to take a log first, then it does that. So this is the great advantage of cumulants, that when you have independent random variables and you look at linear combinations of them, then the corresponding cumulants would add up, and that is one of the reasons why you use cumulants at all. You can generalize this to higher variables, more and more variables. Of course it will not be in such a simple form, but if each of these variables is itself a sum of two random variables and so on, then this thing keeps on telescoping and you have a sum of the cumulants finally. In the case of the Gaussian, the following magic happens. It turns out that if let x1, x2 etc. be independently distributed, they are all independent random variables, Gaussian random variables. So suppose they are all Gaussian random variables, they are all independently distributed. Then it turns out, when you work through this algebra, it will turn out that if you consider z equal to summation ai xi over I. So ai's are some numbers and find a general linear combination of all these guys. Then it turns out that z is also a Gaussian random variable. So a linear combination of any number of independent Gaussian random variables is also Gaussian, its probability distribution is also Gaussian. Now how is a Gaussian specified? It has that exponential distribution form with two parameters, the mean and the variance. So if I tell you the mean and the variance of this sum, that the job is done, finished. So suppose it turns out with mean mu1 mu2 and variance sigma 1 squared, sigma 2 squared, suppose the means of all these are mu1 mu2 etc., the variances are sigma 1 sigma 2 squared etc etc. Then the question is, what is this guy here? It turns out the average value of z, that is obvious, is equal to summation I ai mu I, and the variance of z equal to sigma squared equal to summation over I ai sigma I squared ai squared. So that is it, the answer is also Gaussian and it is specified by its mean value and its variance. In particular, and this is one statement of the central limit theorem, in particular suppose they are all identically distributed variables with the same mean value mu and the same variance sigma squared, then if mu1 equal to mu2 dot dot equal to mu and sigma 1 squared equal to sigma 2 squared dot dot equal to sigma squared, bad notation, so I should not use this variance equal to that, okay, let us not call it sigma squared. Sigma squared is a common variance here. Then z equal to x1 plus x2 plus xn, there are n of these fellows, minus n mu. So you subtract out the common mean, it is clear that this variable would have 0 mean now because I removed that thing here, but you have to scale it by dividing by sigma root n, this quantity here is Gaussian distributed with mean equal to 0 and variance equal to 1. So that is why I normalized it by doing this. And the remarkable thing is that if the variables x1, x2, x3 are not Gaussian distributed, but they have some means and all their variances are finite and the means are finite, then a combination of this kind, a suitable combination of this kind in the limit in which n goes to infinity becomes a Gaussian, even if these guys did not have Gaussian distributions. Just like I said, they had uniform distributions between 0 and 1, but you add up a whole lot of them and the answer will turn out to become a Gaussian, suitably shifted, and that is the content of the central limit theorem. I will at some stage show you how a random walk generates a Gaussian, but this is the whole idea here. It is a very powerful theorem, it is the center of statistics, if you like, sort of crown jewel of statistics is the central limit theorem, because it says if you have some effect which is caused by a number of causes, they are all independent of each other, they are all random working incoherently with each other, then under suitable conditions, fairly general conditions, the effective random variable that you get finally is really going to have a Gaussian distribution, and that is the reason why the normal distribution appears so often in physical applications almost everywhere. So this is the root of it, and there are generalizations of this whole thing here. Notice that I said you could ask, is this the only kind of distribution that is so central to everything? namely I add a whole lot of things, I get Gaussian. Other distributions where if I take identically distributed random variables, they would also give exactly the same distribution when I sum them. Such distributions are known, they are a family called infinitely divisible distributions, such that if you have a whole lot of random variables all identically distributed by some distribution, their sum also has the same kind of distribution. These things for arbitrary values of sums, the number of variables you sum over, they are called infinitely divisible. And a subclass of infinitely divisible distributions are the so called stable distributions, and the Gaussian is one member, an extreme member of the family of stable distributions. Let me explain what a stable distribution is. These are called the Levy alpha stable distributions. There is a technical definition of these distributions, but let me give a simple heuristic definition here. These are distributions for which the characteristic function p tilde of k, the Fourier transform of the probability density function, its magnitude goes like e to the power minus, in the case of the Gaussian, remember the characteristic function was e to the power minus ik whatever it was, plus k squared ik mu, and then there was a minus k squared sigma squared over 2. So the magnitude was e to the minus k squared. The magnitude here is like some constant and modulus k to the power alpha. The characteristic function itself has a phase factor, there is an e to the ik whatever it is, but it is a complicated expression, well known expression, but what we need to know here is that the magnitude goes like e to the minus mod k to the power alpha. Then this makes sense in the range 0 less than alpha less than equal to 2, because you can show that it is only in that range where the inverse Fourier transform of p tilde of k will be non-negative and therefore will qualify to be a probability distribution. Remember, we want p of x to be a probability distribution so that it should be non-negative, and that happens, one can show, when alpha runs between 0 and 2. Alpha equal to 2 is the Gaussian. That is the most well known distribution here, the most familiar and the most famous one. You can also show that it is only when alpha equal to 2 that the variance is finite, the mean is finite and the variance is finite. As you keep decreasing the value of alpha, the moments start diverging, and for alpha less than 2 the variances are all infinite. For alpha less than 1 even the mean value is infinite. Alpha equal to 1 has also got a name, it is called the Cauchy distribution, and what it looks like is the following. So if I look at p of x, this is e to the minus x squared over 2 sigma squared, this is alpha equal to 2, p of x for alpha equal to 1, the Cauchy distribution, apart from a normalization factor, it looks like some x squared plus lambda squared. It is what in physics you call the Lorentzian shape, and the second moment of this is infinite, it is a symmetric distribution, and you find x squared average, you have integral x squared over x squared plus lambda squared minus infinity to infinity, which diverges. So the mean value, the variance of this distribution is infinite, it is too broad. Okay. It is also symmetric. By the way, this is a member of a family of non-symmetric distributions, and the extreme case is in fact this alpha equal to 1, the skew parameter equal to 0, and then you end up with this thing here. You could also say the mean itself is infinite, because you have to do integral x dx over x squared plus lambda squared, but you could say that even though it diverges at the ends, it is still an odd function and therefore it vanishes. So if you took the principal value of this integral for the Cauchy distribution, you could say it is still 0. If alpha is less than 1, this is not true, even the mean is infinite, but it has got practical implications, and I will mention in a minute what they are. I should say right away that there are only 3 cases for which you can write the inverse Fourier transform of this characteristic function in a closed form, in a simple closed form, in terms of simple functions like this or this and so on. The other one is alpha equal to half, and sometimes and very often it is called a Levy distribution itself, not to be confused with the whole family of distributions, stable distributions. And P of x for alpha equal to half looks like 1 over x to the 3 halves e to the minus constant over x, and this is for x greater than equal to 0. So one sided distribution. So while this guy here looks like this, it is a Gaussian, this fellow is a Lorentzian, so it is a little more spread out, this fellow here is 0, dies off. It is very flat at the origin because this thing here goes to 0 very rapidly even though this diverges, and at infinity it goes like 1 over x to the 3 halves. So we can see the mean value of this distribution is infinite because you got to do integral x over x to the 3 halves up to infinity, and that diverges. This also appears in physical applications very often, and there is, as I said, these are members of a whole family, and these distributions have many interesting properties, among which is the fact that if you have a set of identically distributed random variables with this with any of the Levy distributions as a common distribution, linear combinations have exactly the same functional form on distribution. So the law of distribution does not change, and there is a generalized central limit theorem, the counterpart of that for alpha equal to 2, for general alpha there is such a central limit theorem, and as I said these are also infinitely divisible, in the sense that each such random variable could be broken up into any number of pieces, arbitrary number of identically distributed pieces for every n. So that is why these are also called infinitely divisible, and they have many other properties. Okay. Now where would this occur? Well, you know already that if I give you a random variable with a certain distribution, a function of this random variable does not have to have the same distribution. For example, we looked at the Maxwellian distribution there, and that was for Vx, V squared, but if I ask you what is the distribution of the energy of the particle, that does not look like this at all, right. Then what I have to do is to take the fact that the speed goes like e to the minus mv squared over 2k Boltzmann t, and I have to change variables from here. So this is the distribution of the speed in 3 dimensions, that goes like this. But if I now want to look at what is P of the energy epsilon, epsilon is equal to half mv squared, then I have to change variables, and this will become equal to P of v dv over d epsilon, and I have to express the right hand side in terms of energy and so on, and that Jacobian of the transformation also plays a role. And what does this look like? What does this guy look like? Well, it will look like epsilon to the power half e to the minus epsilon over k Boltzmann t, density of states factor multiplied by the Boltzmann factor. And what will this guy look like? Well, this distribution will look like this, epsilon. So it looks very different, and it is not a Maxwellian, and it is not Gaussian or anything. In the same way, if I give you 2 random variables, each of which is Gaussian, and I ask what is the distribution of the ratio of these 2 random variables, that also runs minus infinity to infinity, that answer turns out to be a Cauchy. Or I give you a random variable which is Gaussian, and I ask what is the distribution of 1 over the square of this random variable. So if x is Gaussian, I ask what is the distribution of 1 over x squared. Now 1 over x squared can't be negative, it runs from 0 to infinity, and it turns out to be precisely a Levy distribution. So there are deep connections between the members of the family of stable distributions, and there are deep dualities between these distributions, etc. So this is the subject of considerable development. A lot of mathematics has been done by the statisticians studying these distributions, and it has other implications as well. Regarding the Gaussian, I should make a mention that it rapidly gets into very interesting things, because you could ask what happens if the number of variables is infinite, and then you could ask what happens if the number of variables is continuously infinite, and then you have distributions of functionals, you have Gaussian measures and so on, you have distributions of Gaussian fields as they are called, and that leads to various other applications, including applications in quantum field theory, etc. So this takes off in a different direction altogether, but they all start with this very humble initial Gaussian, the fact that sums of Gaussians are also Gaussian and so on. We have talked only about continuous variables. If you looked at discrete variables, discrete valued random variables, then you have a parallel theory to this, and then you can define the analogues of stable distributions in certain circumstances on the integers, for example. For instance, a Poisson distribution is, it means a random variable takes on only non-negative values. Now you can easily show that the sum of two independently distributed Poisson random variables is also Poisson with means that add up and so on. So certain theorems can be extended to discrete values, but you should not assume that it is automatically true for arbitrary linear combinations, because the difference of two Poisson variables cannot be Poisson, because the difference of two positive integers could be negative. I leave it as an exercise to you to find out what the distribution of two Poisson random variables each with the same mean is, what is the distribution of the difference of these two variables. That difference could take on values from -infinity to infinity over the set of integers. So your exercise is to find out by doing this kind of trick, the delta function trick, except now you should put Kronecker deltas and summations instead of integrals. So let me stop here, and then we will come back and when necessary do some more distributions.